Hello everyone, how's it going? Hope you are doing very well. Welcome to the first session of our course. Our today's discussion will be regarding finding an answer for a very essential question. Why exactly we need to be able to read, analyze, and obviously understand electrical wiring diagrams and electricity. Well guys, let us start by mentioning a point first. All the electrical panels, all the electrical equipments actually contain this, you can say wiring diagram, right? Now, this diagram could actually be set or sketched on a piece of paper, or for example, using a software, a particular software such as AutoCAD or even ePlan. Now, basically, guys, no matter what method we have used for creating the diagram, we should definitely be able to read and analyze it. And this matter is actually going to be our main focus today. Well, guys, the first reason regarding the importance of reading and analyzing electrical diagrams would be the matter of repairing and testing electrical panels. Well, obviously, in such cases, having a diagram could be quite helpful. Let me give you an example. For instance, guys, what we got here would be a diagram of a specific segment or part of an electrical panel, okay? As you can see in the image, we have several parts, several items. To put everything simply, we have several terminals actually. And then we got this main switch at this point. And also there's an automatic switch here exactly. And you know what? Let me give you a realistic view on the models of these items. Here we go. Here we got the terminals that I mentioned. And also, as you can see, each terminal is actually specified through a particular, or actually some particular letters. And here would exactly be where having a diagram could be quite helpful. As in we would understand that, for example, L1, L2, and L3 terminals have moved all the way through this path that we got here, as you can see, and to where exactly this, for example, switch is set, okay? In other words, guys, thanks to this diagram, we can understand what exactly is going on with different parts that we got in this entire electrical panel, okay? And obviously, when we understand what's going on, we can start repairing or testing the equipment that we are working with. And again, all thanks to the diagram that we have, all right? Next up, guys, we can talk about making samples, simplifying, changing, or even reconstructing, whatever you want to call it. Let's just assume that we actually have an electrical panel, which is quite old, it's out of date, and that's why we need to change its structure. Yeah, let's say we need some sort of a renovation here, as in changing the old parts and items with a newer or even newest ones, okay? Now, having a diagram here could actually help us understand what kind of items we exactly got in that electrical panel. And obviously, this way we can find their replacements quite more easily, all right? Now, the third reason, guys, would simply be the matter of learning. Okay, let's say we're trying to learn some terminology in the field of electricity. More importantly, regarding the whole designing process that we need to be familiar with. Now, the thing is, knowing about different types of electrical structures could extremely be helpful for us here, okay? Because, guys, usually these structures would be repeated over and over again in different types of electrical wiring diagrams. And repeating something or going through something over and over again could be obviously quite helpful in, learning anything. Now, guys, let's say we actually need to work with a software, like a graphical one, such as AutoCAD. AutoCAD Electrical, more specifically, or let's say even ePlan, okay? Now, the fact of the matter is, before starting our work with any of these softwares, we should definitely be able to read, understand, and, analyze an electrical diagram. And after becoming predominant in all of this, we can jump into working with these softwares. In other words, guys, we can somehow claim that this whole thing, like knowing about different structures or being able to analyze different types of, wiring and schematic diagrams, could actually be counted as a prerequisite for working with different softwares. And guys, obviously you can't possibly become an electrical design engineer without being familiar with different structures, or even without being able to read, understand, and analyze different types of wiring and schematic diagrams. Because again, guys, don't forget, this is very important. Knowing how to read and analyze a diagram, a wiring diagram, could extremely be helpful when it comes to designing and drawing electrical sketches. Hello and welcome everyone. In the field of electricity, to display how exactly an electrical system functions, we usually use electrical diagrams. Now the thing is, there are actually several types to these diagrams, some of which are extremely useful, some other are simply not that much. Now guys, in our today's very short session, we're just basically going to be introduced to some of these different types of electrical diagrams. Well guys, the first diagram that we can mention here, which is actually the most common, important, and useful diagram in the field of electricity, would be wiring diagram. Then the second type of diagram would be SLD, or single line diagram, also known as one line diagram, as you can see in the image. As for the third category or type, we have ladder diagram. And for the fourth type, we have cabinet layout and components arrangement. Now guys, basically these would be the types of diagrams on which we're going to have a discussion in our course. Alright guys, welcome back. Let us continue our work regarding different types of diagrams. So far we talked about wiring diagrams. Now let's discuss SLD, or single line diagram. Now sometimes guys, we might need a view on our electrical system, something like a general view. I mean, something without many details, okay? And this would be where exactly we can use an SLD. Basically guys, in such diagrams, we would see several lines, horizontally and vertically, representing, for example, single-phased or even three-phased lines, okay? Now, take a look at this line up here, this, entrance line up here. This could, in fact, include like 3 or maybe even 4 electric power lines. Now, the same thing might go, for example, here. Well, I guess what I'm trying to say here is that the lines that you can see here in this diagram, in this SLD more precisely, might include several electrical lines, in fact. And by the way, guys, we actually got several electrical symbols as well. Like, for example, this symbol up here actually represents a breaker, a switch, okay? And also the same goes actually for this symbol. Then we have a symbol for the contactor, or even we have a symbol for protective elements, as you can see here. So guys, what we can get from all of this is the fact that in SLDs, or single line diagrams, we actually have some specific electrical symbols, all right? And also, no matter how many lines we actually have, they would all be displayed as single lines. Now, let me show you another example on such diagrams. All right, here we go, guys. The SLD that you can currently see here is for starting a three-phase motor. Now, let's see what exactly we got. For example, up here, there's this main electrical current, or precisely a main path or a main flow here. And well, there are some further information up here, like for example, 3200 ampere for current. And then for the voltage, we have 415. And also, it includes 3 lines, as you can see here. Alright guys, let me show you something regarding this current here. It might actually look like something like this. And well guys, to explain this even further, there are some feeders here, and all of them are connected to some other elements and electrical equipments. Like, for example, to this breaker, to this switch, which by the way is in fact an MCCB switch. And then also there's a contactor here. What else? There's a transformer, and then measuring equipments, as well as protective equipments, on which we're actually going to have a discussion later on. Oh, and don't forget there's a CBCT transformer down here. So yeah, basically guys, for creating such diagrams, instead of drawing several lines, just stick with using a single line. Now, by the way guys, there are some graphical softwares that we can use for creating such diagrams. For example, we can use the ePlan software for creating SLD or single line diagrams quite easily. Okay everyone, welcome back. Moving on in our discussion regarding types of diagrams, we reach ladder diagrams. Well, the diagram that you can currently see on the viewport here would be an example on them. And by the way, this specific diagram that you can see is for a control circuit, and it includes both start and stop push buttons, and also there's a bobbin or a contactor. And well guys, there are some complementary points regarding all of these parts, items, and segments that we're going to go through in our future sessions. Now guys, basically ladder diagrams are like a very simple circuit such as this one here. Like for example, there's a phase line that's going to be connected to some sort of a switch from one side. And then also there might be a lamp, for example, like this. And then it'll be connected to this neutral line here. And well, we can basically use the switch here to turn the lamp on and off. Now guys, just like other diagrams, in this type of diagram, we're also going to see some emplacement areas as well as some specific symbols. Now for further elaboration, this would be the start push button, for example. And then this symbol represents the contactor and where it's going to be set. Now guys, in programming language, there's actually a concept called ladder language form in PLC. Now, the thing is, there's actually a similarity in between this specific language and ladder diagrams. Now guys, if you're familiar with the whole concept of programming, you know that we actually have a language called ladder language. If this is the case, guys, you might already know that in appearance, when it comes to appearance, ladder languages and, well, ladder diagrams that we would see for electrical systems are quite look-alike. And well, to be honest guys, they are quite useful in this entire field. In the field of electricity. Alright everyone, moving on, we have reached components arrangements and panel layouts. Well guys, for one thing, these types of diagrams are not really related to the whole wiring systems, okay? Basically guys, these diagrams would only give us the location that we need for setting the equipment. Hence the whole diagram's name. Using such diagrams, we would understand where and how exactly an electrical equipment is going to be set in our electrical panel. Right, let me give you an example. Check this out. The panel that you can currently see here is actually called the capacitor panel, all right? Now here, we got equipments such as this regulator. Yeah, we can see the equipment and its emplacement area. And then also there are some fuses, some protective switches, if you will. And well, they are specified right in this area, like how they are arranged actually. And right over here, we actually have a view on the capacitors themselves. And as I said here, we got the contactors. And well, the arrangements of other equipments and components are specified here as well. And by the way, guys, down here we have, how do I put this? Well, let's go with what we have in the image, actually. We have a front door view. More precisely, when we open up the door, we can get a front view on the equipments and their arrangements. And well, the same goes for back and side views. And well, obviously, guys, this could become quite handy when we are working on electrical panels. All right, moving on, let's see what else we got. Okay, take a look at this. Guys, alongside components arrangements, we also have cabinet layouts. Well, guys, through this, we can basically get you can say a general view, a general layout on the entire electrical panel. For example, this current one includes 7 cells, with each cell containing a feeder. Like, more precisely, each one of these equipments is actually a feeder. And well, they would basically be used for controlling a single-phased or 3-phased motor or direct current motor. In other words, a DC motor. And then in this cabinet layout, we can see emplacement areas or locations for other equipment such as push buttons or for signal lamps or even for circuit breakers, aka power switches. And yeah, basically these would be the information that we can get out of these diagrams. Alright everyone, welcome back. So far we discussed different types of electrical diagrams. Now let's start talking about different types of sheets that we have for them. So we're going to mention these different sheets as well as the information that we can get out of them. So yeah, without any further ado, let's start talking about the important and essential sheets that we have when it comes to electrical diagrams. Alright guys, the first sheet that we can mention that we can talk about is called a cover sheet. Now basically the information that we can get out of these types of sheets would include some general information regarding the type of the diagram as well as the designer. Then the second type is called index. This one would give us a list of everything that an electrical diagram contains, alright? Then in the third place we have legend. Now there's some sort of a list form to these types of sheets as well, but the thing is, legends are more like a guide which cover the electrical symbols, like the lines that we can see in an electrical diagram. The fourth type of sheet is called bill and materials. This one has tables containing, for example, the number and also the type of the materials and equipments that we have used in an electrical diagram. And number 5 is called the drawing sheet, guys. We can use this one for setting the sketches that we need for creating a diagram. It might contain, for example, items such as, well, single lines or multiple lines, hence the name drawing. Now, number 6 is called X sheet. This one contains only the terminals that we might need for creating a wiring diagram. And lastly, number 7 is called Z sheet. Now in this type of sheet, we can find stuff such as, well, some symbols or like the type of the equipments that we have used and basically just more information or more details on the stuff that we have set in the drawing sheet. Okay guys, in our previous session, we mentioned the name of the sheets that we have. Now let's start talking about them one by one, starting with cover sheets. Now, there are several information that we can get out of these sheets. For example, number 1, the type of the electrical diagram. Number 2, how many times the diagram has been modified and, well, by whom actually. Then, number 3, we can find out who, as in a person or even a company, has ordered the designed diagram. And number 4, how many sheets this diagram, this plan exactly has. Alright? Now guys, let me give you an example on cover sheets. Alright, take a look at this. We have a cover sheet here containing some specific information and characteristics on an electrical panel called switchboard. Now, switchboard is an electrical panel that would be connected to an incoming power. An electrical power more specifically. And then through the switches and also the bus bars, that incoming power would be converted into outgoing power and then it will be distributed through the whole system. Now, as I said, we have some specific information and characteristics here. Let's try going through some of them, like 1 or 2 of them, to see what exactly they are. Like, for example, these would specify the dimension, you can say, or the size of our electrical panel. Then, for example, we have the color code of our panel here. Then we have the protection degree against matters such as humidity, dampness, or even some extrinsic factors. We can also find out whether this electrical panel got any gland plates or not, which this one actually has. And then another factor, detailed characteristic, whatever you want to call it, that we can see here would be the matter of thickness of the sheets that have been used in this electrical panel. Then the switchboard's connections are set in the back. As you can see, it says rear. And let's see what else is important, what else we can talk about. Well, the switchboard's current, yeah, we can talk about that. The maximum current that goes through the bus bars here is 4,000 amperes. Then we have 400 for the voltage. We got 4 poles, more precisely 3 phases, and also 1 null or, well, neutral. For control circuits voltage, we have 220 and 110 volts. By the way, guys, AC and DC stands for alternative current and direct current. Then, guys, we have air as the insulation used in between the vertical bus bars. And, well, obviously, we need an insulation for the horizontal bus bars, which here, as the insulation, we have thermofits. And, well, there's air also. And by the way, guys, if you don't know what exactly is a thermofit, well, we can say that there are some particular insulations that we use for bus bars specifically. And you can actually see an image on them here as well. Anyway, here we got the size of the utilized wires in the control segment. Oh, and we got the size and also the material used for the bus bars, which is copper here. And, well, you can actually see the sizes as well. What else? Oh, we got the coating for the bus bars. These would usually be set on the bus bars themselves. We got L1, L2, and L3. These would actually create our 3-phase system. And at the end, we have this color specification for the earth, which is yellow or green. And yeah, that would be all, guys. This was an example of cover sheets and, well, the information that we can get out of them. All right, everyone, moving on to the third type of sheets, we got index, aka master list. Now, before we start, guys, let me mention a point real quick. When we are working with a software such as, well, let's say ePlan, more precisely, when we are using it for example, drawing or setting some sketches for a system, after you're done and you want to create your output in the software itself, you can actually find an exporting option called master list or, well, as you know, index sheet. Now, what exactly we got in the master list? First, we got a list of sheets numbers. Then, secondly, we got a very short and concise, well, we can say explanation or elaboration on what exactly is going on in that specific sheet. Okay, now guys, this would be an example of a master list or an index sheet. As an information that we can get out of this, for example, in page or sheet number 4, we actually have a legend, as you can see here. Or as another example, in number 10, we got a starting circuit for a 3-phase motor. Now, question, guys, how exactly we can understand that this is actually a starting circuit? Well, from this term here, motor feeder. And by the way, guys, this whole master sheet is actually for an MCC electrical panel. Let me just write it down for you. MCC, as in Motor Control Center. Well, currently, you're not going to get what exactly this means. Don't worry, though. In our future sessions, we're going to talk about not only this, but also many other different types of motors more completely. Okay, everyone, welcome back. The next type of sheet that we can talk about is called legend. The information that we can find in a legend sheet would include, first, the symbols of the items that we actually have in an electrical diagram. Number 2, a description, or you can say some sort of an explanations on the abbreviation that we can usually see in diagrams. And in the third place, we have some sort of a coding or just a numbering method for all the items and equipments that we actually have. Now, as an example, there's a legend containing several electrical symbols. More specifically, this is a legend with some tables containing all the symbols that we actually have in this entire project, or all the sheets in this project. Or as another example, I have another legend to show you here. For example, let's actually go through it a little bit further. Like, regarding the bus duct system, each bus duct actually has a specific color to it. Or for example, let's say for the cable support system up here, again, we have color specification, but this specification actually includes the type or the pattern here as well. And well, obviously, if you pay more attention, you can find more electrical symbols, and also we have some special electrical equipments here too. And yeah, basically guys, using these sheets you can find such information, which by the way are quite helpful. Alright everyone, let's discuss bill and materials sheets. When we are designing a system, guys, we obviously would use some specific items and equipments. Now, in these sheets, guys, we can find, for example, a list of all of those utilized items and equipments. And well, regarding their appearance, they would usually appear like the one that you can currently see here, all right? Like we get a symbol and then the name of the actual material, which by the way, here we got MCB switch or breaker. And then a very short and brief description on the material and the quantity or the exact number of this material that we have used in the entire project. And at the end, we can find the name of the company, the brand, or basically whoever can be called the manufacturer. And by the way, guys, such lists could also be called part lists as well. Now remember, guys, if you're using a software such as ePlan for designing your system, when you're done and you want to create your output, from your exporting options, you actually have an option that you can use called part list. Now, the thing is, if you do choose part list as your exporting option, it would actually be presented with a table such as this one that you can see, and also with an Excel format. And then you can easily use the exporter table in any way that you can or, well, that you need. Alright guys, let's talk about one or maybe even the most important type of sheet that we have, drawing sheets. Well, there are some specific segments and parts to these types of sheets, and in this session, in this video, we're going to talk about the most important ones. For example, down here on the right part of our sheet, we have this box. And in the box, as you can see, it says title box or title block. Here, we would specify information such as the type of the diagram, or for example, the usage, or even the designer, the name of the designer. It could be a person again, or even a company. Then up here, we have revision history block. Here, we would give information regarding the date of the modification and edits applied on the diagram. The entire drawings would be set in this area. And the most important parts of the drawing sheets would be the zones. Now, another important factor in these sheets would be the matter of addressing. And to do so, we usually use numbers and letters. When it comes to using numbers, mostly numbers from 1 to 10 are used, or even maybe 12. And regarding letters, we go somewhere from A to H, or again, maybe even further. Now, let me try to elaborate a little bit more on this, so that you'd understand the concept of zones better. Okay, take a look at this. There's an equipment set here with this kind of symbol, all right? Now, the address of this equipment here would actually be E2. Or we have another symbol this time down here, and the address for this one is actually B9. Okay, now to make sure that you have gotten everything completely, let me go ahead and give you another example, this time using a real wiring diagram. Okay, take a look at this. Here in this diagram, I have specified two areas for you. The first area would be here, this zone right here. Okay, let me try to mark it a little bit better. This equipment. Also, let me zoom in on it. Okay. Now, the address here would be, let me write it down, O or 0 slash J9. Okay? Now, this 0 here, guys, means that this whole closed contact, the exact same equipment, has actually been used in another sheet somewhere else. All right? And, well, the J9 here actually stands for the exact address of this equipment. So, if we go to this address, if we take a closer look to this exact address, which I guess would be right here. Let me also mark this. Okay, you'll see the exact same equipment here as well. And well, next to it, we can also see 0/G3 this time. Let me write it down completely. Okay. So again, we have the exact same equipment that we have used before in J9, but this time we have used it in G3 instead, right? So the same closed contact or the same equipment. So guys, in these sheets, we would basically see some symbols, and next to them we would see some addresses consist of letters and numbers, which would work as some sort of a referral, you can say. Now, there's actually a name, or, well, it's better to say a term used for such phenomena. When the equipments are referred to each other through their addresses, we call such phenomena cross-reference. And by the way, guys, remember, if you are using some specific software such as ePlan, you can say, for your works and projects, you should know that such things like this cross-reference will be done quite automatically for you. Alright guys, welcome back. Let us discuss X sheets. In such sheets, we would usually find, well, descriptions or explanations on the terminals that we have used in an electrical diagram, and also other information, other details on such terminals, for example, their series, like X100 or X200, and also specific numbers that would actually work as markers for each terminal. Now, as always, let me go ahead and give you an example or show you an example on X sheet this time. Okay, so there's two sides actually to this sheet. One side with letters, another side with numbers. Now, to elaborate a little bit further on this, for example, the series that we got here would be X2. And we have these numbers. As I said, it is quite obvious what they are. They are markers. Now, remember, guys, this part covers the interior part of our panel. And, well, through the addresses that we have here, we can understand, or we can find out where exactly or to which equipment exactly these terminals would be connected. And, well, obviously, this part down here covers the exterior part of our panel. Now, remember, guys, the same thing is actually happening here as well. The same thing as in the interior part. However, this time, the equipments, the targeted equipments, are set in the exterior part of our electrical panel. Alright, everyone, the last type of sheet that we'll be discussing is called the Z sheet. Well, as you can see, I've actually prepared this example for you here, and, well, I'm going to try to talk about the type of the sheet or explain the type of the sheet through this current example of ours. Well, as you can see, first and foremost, guys, we can see some symbols here as well as their context, and also there's some, you can say, side pieces as well. Then in the second column here, you'd actually find a very short and brief description of the symbol. Then we have the type of the symbol, like what kind of model we got here. After that, we have the manufacturer's name. Like here, we can find out what kind of brand we're exactly working with, all right? And finally, at the end, we have the designation column. Here, we would find some letters and numbers specifying the symbol, or, in other words, distinguishing the utilized equipment. Now, remember, guys, the graphical softwares that we would usually use for creating or, well, designing an electrical panel have the ability to give you or, well, create a Z-sheet export for you. So, you can easily create an output for yourselves containing information like the ones that we have gone through in this session. Hello everyone, hope you are doing very well. Welcome to another session of our course regarding electrical diagrams. Today, guys, we'll be discussing some points, well, very important points actually, regarding different segments of electrical diagrams that could be quite helpful for us when it comes to analyzing them. Well, as you can see in the image, guys, electrical diagrams or, well, electrical schematics consist of four main parts, so four main components. Again, you can see these four components in the image. They are symbols, lines, words, and numbers. Now, through combining some of these main components, we can actually get some side components. To elaborate on this, for example, when we combine words and numbers, we can get side components such as device tags, wire tags or wire labels, and also electrical abbreviations. Alright, now let's go through some examples regarding these. Take a look at this diagram here. Now, in this diagram, we actually got so many components. For example, we have symbols. Let me try to mark them out for you. All of these are examples of electrical symbols. See, when we say symbols, we're in fact talking about these items. Also, we got lines. Now, guys, the thing about lines is that they might appear differently, like they might have different patterns to them, which is exactly the case, or which is exactly what's going on, what's happening in this current diagram of ours. Now, as I said, words are another type of main components that we can actually see here. All of these are examples of words as main components. And well, the last main component, the last type of main component that we can see in this diagram would be the numbers. Let me also mark the numbers for you as well. And yeah, guys, basically these were some examples regarding all the main components that we can find in an electrical or a wiring diagram. However, we're not done yet. Earlier in this very session, we said that through combining these main components, we can create side components. Like, more specifically, we said through combining words and numbers, we can create side components such as device tags, electrical abbreviations, and also wire labels. Now, we can mark these as an example for device tags. Okay. And after that, let's see what kind of electrical abbreviations we have. Like in this tag that we got here, the letter Q or the letter S, which stand as an abbreviation. What else? Up here we have LP. And, well, yeah, basically that would be it. Now, let's see what we have for wire labels. Yeah, wire labels, aka wire tags. Now, as an example, we can mark this out. And yeah, guys, that would be all for now. Basically, these were all the main components as well as side components that we can find in an electrical diagram. And well, later on in our future sessions, we're going to talk about these more completely. Alright guys, welcome back. Let us discuss electrical symbols. Now, first off, guys, for drawing an electrical diagram, we have a variety of standards worldwide. And one of the most important standards would be IEC or International Electrotechnical Commission. Now, IEC standard number 6617 part 2 to 13 includes a database containing or, well, displaying the electrical symbols, alright? And well, through this database, or with the help of this database more precisely, we can draw our electrical diagrams. Now guys, a point worth mentioning here is the fact that basically electrical symbols are divided into two categories. Category number 1 is called multi-line symbols, alright? And category number 2 is called single-line symbols. Now, obviously, single-line symbols are used in single-line electrical diagrams, and multi-line symbols are basically used in wiring diagrams, okay? Now, as an example, here we got a MCCB circuit breaker. Now, when it comes to creating or drawing an electrical diagram for this sort of breaker, we can actually go with both single line symbols and multi-line symbols, okay? I mean, obviously, according or based on the standard, based on the IEC standard. Alright guys, this was a very short and concise introduction to this concept. Later on, we're going to talk about it more completely. Okay guys, let's talk about the electrical symbols in more detail. We're going to start by start and stop push buttons. Now, let's see what kind of components or, well, sub-items we got in such equipments, in such buttons. Like, what exactly they are made of, and, well, then after that, let's see how they work. For example, we got this copper-made bar, and then there's a couple of contactors, and then a spring set underneath the bar. Now guys, the first image is titled Normally Opened. This means that there's no electrical connection in between the contactors. Now guys, when we push this bar down, that electrical connection would be created in between the contactors through the bar, obviously. And as a result, an electrical current would be created and it would move from one contactor all the way to the other one. And when we remove our finger, in other words, when we stop pushing the button, the electrical current that we created would simply stop. All right? Now, let me move to the next slide. Here we go. Now, what we got here, guys, is a real image of a start-stop push button. Also, there's a couple of terminals, number 3 and 4. And, well, according to the IEC standard, this would be the exact symbol that we usually use for such push buttons. And this one would be the symbol that we usually use if we are working based on NEMA standards, which is an American one. Okay, now I've prepared a clip for you as well. In the clip, you can see how exactly these buttons work. Here we got the terminals, number 3 and 4. And, well, there's a green button set on this side. When we push it down, one of these two might happen. I mean, we might open the contactors. I mean, we would create normally open, or we might close them down. Right, moving on to the next slide, we have the stop push button. Now, first and foremost, guys, the normal version or the normal mode for these sorts of buttons would be this one that is in fact titled normally closed. So, in fact, we can get that the electrical current is actually moving in between the contactors, in between the terminals. And exactly the same as in the last button, if we go ahead and push the button down, the electrical current would simply stop. And obviously, when we stop pushing the button, when we remove our finger, the electrical current would appear again. It would be created all over again. So that's the reason why we exactly call this stop push button a normally closed push button. All right? Now, again, in the next slide, we can see a real image for such equipments, for stop push buttons. Again, we have a couple of terminals, this time number 1 and 2. And again, we have two versions for its electrical symbols, one from IEC standard. And as I said, this symbol would be the American version. Now, let's check another clip as well. Let's see how exactly this button works. As you can see, we have the terminals, number 1 and 2. Then on the other side, we have another button. This time, instead of green, we have red. And as I said, we can use this button for stopping the electrical current. And again, guys, remember, the normal situation of such buttons is actually normally closed. And when we push it down, we open the contactors. By the way, guys, both start and stop push buttons are actually counted as an extremely useful electrical equipment. And, well, we're going to discuss and understand this fact more completely later on. Welcome back, everyone. In this session, we're going to talk about contactors and relays. Now, what we can see in this image here would be the constitutive components of a contactor. or we can say the way or the basis of how they would exactly function. I mean, for example, there's this magnetic coil here. The endpoints of this coil are named as A1 and A2. Then there's a metallic core set on top of this coil. And also, as you can see, a spring is actually wrapped around this metallic core, all right? Now, the top part of the core is connected to this copper-made bar. And by the way, this bar is also called the copper contactor. Now, although we call this a magnetic coil, this would become magnetic, truly magnetic, when we connect it to a specific voltage. Now, the thing is, this voltage could be an AC one, or it could be a DC voltage. Now, when the coil becomes magnetic, it'll start pulling the core, and after that, the copper contact would be pulled down as well, and as a result of all of this, an electrical current would be created. All right, let us move on to the next slide and continue our discussion. Let's see what we got. Okay. Here, we got an image of a contactor. First thing that we can talk about would be the terminals. We have 4 of them, L1, L2, L3, and 13. And then on the side, we have T1, T2, T3, and 14. And regarding the image, the terminals are set right over here. Now guys, what needs to happen is that the set of terminals that we have up here should be connected to the terminals below them through contactors. Now, in the first image, in the first version that you can see here on the left, these terminals are actually normally open. And if we go ahead and connect the voltages, the specific voltage that we have, to A1 and A2, the terminals would start connecting. And well, it's going to go through like this. L1 terminal would be connected to T1, L2 to T2, L3 to T3, and at the end, 13 to 14. Okay, so yeah, the terminals are connected, but what now? What's the usage? Well, let's find out. Through using a contactor, guys, we can, for example, connect these terminals, L1, L2, and L3 more precisely, to a 3-phase. And for the other side, for these terminals, T1, T2, and T3, we can, for example, connect these to a 3-phase motor. Now, when the bobbins are getting activated, more specifically, the A1 and A2 terminals are getting activated through connecting a voltage to them, like 230. The terminals are getting connected. And I told you, L1 would be connected to T1, L2 to T2, and L3 to T3. And this would start up the motor. Okay, now let me move on to the next slide. All right. Pay attention, guys. The contacts that we have in between these terminals, the contacts that would connect L1, L2, and L3 to T1, T2, and T3 more precisely, these contacts are what we actually call the power contacts. But we have another contact, a contact that would connect terminal 13 to terminal 14. Now, this one is a contact that we actually call an auxiliary contact. Now, just know that these contacts are mostly used in control circuits. And, well, if you don't know what they are, or if you don't know what I'm talking about, don't worry, because later on we're going to talk about them in more detail. For now, let's just stick to our own discussion. Now, guys, sometimes when we look at our system, in between the contactors that we have, we might find a normally closed one, like the one that you can see here in the image. Now, they would usually be specified by numbers such as 21 or 22, exactly like what we have here. And, well, you know what, guys? Just be aware of this. Yeah, that would be enough for now, because later on we're going to talk about all of these more completely when we reach control circuits. Alright guys, let me give you a point regarding contactors in power circuits. Basically, we have two types of contactors. A normally open one, and you can see its symbol is schematics. Here, this would be the IEC symbol and the NEMA or the American symbol. And we also have a normally closed contact, as in the second type, obviously. Now again, we have the IEC symbol and also the NEMA symbol. Okay, let's move on to the next slide. Okay, here we can see two symbols for the contactors, IEC and NEMA, obviously. Then this would be the bobbin of the contactor, and it is usually specified with K1M, K2M, K3M, and so on. Now we have two terminals set on both sides of the bobbin, specified by A1 and A2, as you can see. One side would be connected to phase, the other one to null. And for specifying the other terminals, we actually use numbers like 1, 2, 3, 4, 5, and 6. If we are working based on IEC standards, remember that. And well, these are actually the terminals that we saw before. The L terminals and T terminals. Now, let's talk about the symbol that we have when we are working based on NEMA standards. For specifying the bobbin, first off, we would use, for example, M1, M2, M3, and so on. And normally open contacts are specified like this. Most specifically, the power contacts. Right, moving on again. Now guys, if you remember, we said that we might have auxiliary contacts in our system as well. Now, if this was the case, this is how we would display them. Again, we have the power contacts right here, and these would be the auxiliary contacts, which, as I mentioned a few minutes ago, we would usually find them in control circuits. Now, just like what we did in our previous session, let's watch a clip to understand everything better. In the video, we'll get a close-up view on the contactor. Like, for example, we got the terminals here, the L terminals, and then on the other side, we have the T terminals, okay? Then we have the bobbin terminals, more precisely A1 and A2. We also have the auxiliary contacts, terminals 13 and 14, and, well, as well as 21 and 22. And by the way, guys, we are able to activate this contactor quite manually, and it would be completely like this quite easily. And yeah, that would be all, guys. That would be all for the concept of contactors. Hello guys, welcome back. In this session, we'll be discussing three-phase electric motors. First off, these types of motors are one of the most useful ones in the field of electricity, and as an example for them, we can mention squirrel cage rotors. Now, usually such motors contain 6 terminals in them, and their names would be as following: U1, V1, W1. And on this side, we would have W2, U2, V2. Now, let's take a look at some images to understand how exactly connections could be created in such motors. Now, there are actually 2 ways for connecting the terminals in a squirrel cage rotor, in other words, in a 3-phase motor actually. Now, the first way, or the first method for creating the connection is called star. In this specific method, first off, the lower terminals would be connected, talking about W2, U2, and V2. And then the top terminals, more precisely, U1, V1, and W1 would be connected to 3-phased lines L1, L2, and L3. And then the motor would be turned on. Alright, the second method is called the delta. Here, U1 would be connected to W2, V1 to U2, and W1 to V2. And also, again, the top terminals, U1, V1, and W1, would again be connected to three-phase lines L1, L2, and L3. Alright, now guys, remember, we are able to use both methods here, but if we want our motor to have full power, we should actually use the delta. Alright guys, in the last slide, we can see the symbols that we have for such motors, both the IEC version and the NEMA, or the American version. Alright guys, in this session we're going to talk about a specific protective equipment in the field of electricity. More precisely, we use this equipment for protecting the single-phase and three-phase motors. Now this equipment is called bimetal relay or overload relay. Now, first and foremost, let's see how exactly this relay works. Before we start, let's answer a question real quick. What exactly overload is? Well, when we connect our three-phase motor to three-phase lines, normally an incoming electrical current would be created, alright? Like, for example, the motor could start getting, 10 amperes of electrical current. Now, during so, a problem might appear in the motor. For example, we might face a problem with the motor's bearing, or even an overload on the motor's axis, for example, And, basically, as a result of some problem, the electrical current would be increased from 10 amperes, let's say, to 16. And overall, this exact phenomenon is what we call an overload. And in case we don't control it, it would be quite problematic. Like, for example, it might harm the coil in the motor. Now, let's take a look at some situations in which overload could actually happen. Well, in the first situation, the connection that we need for the motor might not be done correctly. We call this incorrect coupling, and you can see it here as well. In the next situation, an extra load would be added to the motor's axis or the motor's shaft, as you can see here. More specifically, an additional load more than the motor's actual power. And then lastly, in the third situation, we might face a problem with motor's bearing, which is actually noted here as bearing failure, okay? And overall, these three situations could cause our system to simply overload, alright? Now, let's move on and, talk in more detail, guys. Okay, take a look at the image here. Assume that we have two pieces, one iron, the other one brass, and they are connected together. And an electrical current is moving or passing through them. Now, when the mentioned electrical current increases, the electrical current that is moving through this piece increases, first and foremost, the temperature of these two pieces would be increased. And, the created high temperature would causes the contact to bend, just as you can see in the image, okay? And as a result of this bending, the electrical current would be cut off. It would stop completely. Now, guys, let's go ahead and see how exactly we can protect our motors in case of overloading. Okay, let me change the slide. Okay, let's see what exactly we got here. In the normal situation, the electrical current would be 10 amperes. And again, in the normal situation, we have three of these contacts set in the path of our electrical current, okay? Now, let's say the overload has happened. The electrical current has increased from 10 amperes to 16. And as I said, because of the high temperature that would be created, the first thing that we would detect would be the bending in the contacts. And well, once more, as I mentioned a few seconds ago, when this bending happens, the electrical current would be disrupted. It would be cut off. And well, obviously the motor would stop working. It would be turned off. Now, let me move to the next slide before we continue. Now, bimetal relay or overload relay. First off, this would be its interior structure. More precisely, we have 3 contacts set in between the terminals L1, T1, L2, T2, and L3, T3. Now guys, through a specific mechanism, these contacts are being connected to a couple of more contacts here. One of them is normally opened, the other one is normally closed. Now, we have some specifying numbers here as well. We have 97, 98, 95, 96. And again, guys, this is important. Don't forget this. We have 2 types of contacts. One of them, more precisely, this one is normally open, and the other one is normally closed. Now, when overloading starts to happen, when the bending in the contacts would start shaping up, the normally open contact, this one, would be closed, and the other one would act in reverse. The normally closed one would be opened. All right. Let's move on. Now, how exactly they work in a circuit? Well, normally, the electrical current, more specifically 10 amperes of electrical current, turns on or starts the motor. And after that, we actually need to set an equipment here called a signal lamp. Then there's a phase line here that is actually connected to this contact here, 97, and 98 is connected to the signal lamp. And the other side of the signal lamp is being connected to the no line. Now, in the normal situation, the signal lamp would actually be turned off. And immediately after overloading would be started, immediately after this specific bending in the contacts would be started, the electrical current would be cut off and the motor would be turned off. And as a result, the normally open contact would be closed down, 97 and 98, and the signal lamp would be turned on, which actually is a warning which tells us that the motor is overloading. All right? And by the way, guys, normally there's a yellow color to these signal lines, and well, we can usually find them set on the doors of our electrical panels. Okay, let's move on. Okay, everyone, so far we successfully found out how exactly a bimetal relay, aka an overload relay, would function. Like, more specifically, we said that we have three terminal sets up here, talking about L1, L2, and L3 more precisely. And then on the other side, or down here, we have T1, T2, and T3. Then we said we have a couple of more terminals set here. 97, 98, 95, 96. We said 97 and 98 are normally open. And the other two, 95 and 96 are normal closed terminals. Okay? And well, by the way, guys, remember, we usually use these terminals in control circuits. Okay, moving on to the next slide, Again, we're going to see a clip. Okay, let me play it out. What we have here, up here, we have L1, L2, and L3. And here we got T1, T2, and T3. And then here we got 95, 96, and also 97, 98. Alright, now let's take a look at how we can connect a bimetal to a contactor. Well, let's take a look at the schematics that we have here. L1 would be connected to T1, L2 to T2, and L3 to T3. Right, and also let me play a video on this as well. So basically, guys, the T terminals set in the contactor would open, and then we can set the bimetal and use some screws to connect it completely. Again, these would be the L terminals, and down here we have the T terminals. Okay, guys, let's move on to, I guess, the last slide of ours. At the end, we're going to take a look at the symbols that we have for bimetal relays or, well, overload relays. As always, we have two versions, the IEC symbol. And by the way, guys, this here represents the power circuit, and this part represents the control circuit. And well, obviously, we have the NIMA symbol as well. And again, we have the power circuit as well as the control circuit. Welcome back, guys. Another type of equipment that we usually use for protecting our electrical motors would be fuse. We usually use fuses for two purposes. Number one, or actually mostly, for controlling and protecting our motors when we have a short circuit, and number two, when we are facing overloading in our motors. Now, first off, let's see what exactly is a short circuit condition. Alright, guys, let's assume that we are working with a three-phase system, okay? And well, for any reason, L1 would be connected to L2. Or, it could be another one, like for some reason, L3 would be connected to L2, okay? So, no matter the reason, basically we call these situations, these conditions, short circuits. And well, as I said, in these conditions, fuses could actually protect your motor. And also, if one of these lines got connected to null, this would also be a reason for creating a short circuit condition. And in this case, again, for example, this fuse here could protect your whole circuit. Now, kind of the same thing happens in a single phase system. As in, for any sort of reason, the phase would be connected to the null. And again, a short circuit would be created. And well, obviously, once more, you can use the fuse for protecting the circuit. Now, guys, we have many different types of fuses, but one of the most important and, well, famous models would be NH. Well, in this very slide, you can see how exactly these fuses look like. Now, this would be the base on which the NH fuses would actually be set. And well, when we assemble the whole thing, when we set the fuse on its base, this would be what we are going to see. Now, we actually have a variety of NH fuses as well. They would actually be divided into different types based on the letters that are used for naming them. Like, we got general fuses that are usually specified through GLOGG. Then we have the motor protective ones that are specified through AM. As for the third type, we have fuses, semiconductor fuses, and they are usually shown through letters such as AR and GR. The fourth type would be regarding solar PV protection. They are shown by GPV. And the last type would be battery protection fuses, and they are shown by GS. Okay? And well, as always, guys, let's take a look at the symbols that we have. I mean, electrical symbols that we have for fuses. This would be the IES. And, well, the other one would be NEMA, the American symbol. Okay, guys, the next type of protective equipment is called the MCB breaker. Now, just like what we had in fuses, these switches, I mean MCB breakers more precisely, they would actually protect your circuit or your system against both overloading and short circuits. They would usually support a range of electrical current from 10 amperes to 200. And when it comes to the number of their terminals, they would simply be divided into two categories. We would either have a single pole or a 3-pole. Now, guys, we have two types of IEC symbols for MCB breakers. Why? Well, because as I said, the breakers themselves are actually divided into two categories. Let's say we are using a single pole one. In this case, this would be the IEC symbol that we need to use. And well, if we were using a 3-pole breaker, obviously we need to use another symbol, which would be this one more precisely. Alright, this was for IEC. Now let's see how the American symbol is going to be, I mean, based on NEMA standards. And well, as you can see, we have both versions of single pole and 3 poles. Welcome back, guys. Let's talk about another breaker. This one is called MCCB. I mean, the last one was MCB, this one is MCCB, so pay attention, don't get confused. Well, to be honest, they work kind of the same, but the difference is that MCCB breaker supports a very high electrical current. And compared to MCB breakers, this one actually has some additional sub-items, you can say. Well, as for the similarities with MCB, this one also protects the circuits against overloading and short circuits. Alright, now let's talk about this breaker in more detail. Alright, first off, we have a switch here, and it could be set in 3 modes: on, off, and trip. Well, obviously anyone knows what happens if you go with on or off. So let's just talk about the third mode. Well, first off, guys, in this situation, the breaker has in fact detected a short circuit or an overload. And by the way, guys, this third mode, I mean the trip mode, would be set somewhere in between the on and off mode. Now let's try elaborating on this even further. As you can see, we have 3 types of trips. For example, let's talk about magnetic trip. Yeah, this one would appear if a short circuit was detected by the breaker. And then the second one, thermal trip, would appear or would act if we had an overload. And number 3 would be manual trip. This would happen if we set the switch on trip ourselves. Because, well, for any reason, because we had to, basically. And by the way, there's actually a specific method for doing this. I mean, for setting the switch on trip manually. Like, there's this red button here. You can push this down. And well, this way, the switch would be set on trip. More specifically, manual trip. Okay, let's move on. In the next slide, guys, we would see 2 symbols. One for thermal elements regarding overload, and the other one for magnetic elements that would be for short circuits. And well, what is important for us regarding these 2 symbols would be the fact that when we combine these 2 symbols, we can actually create a symbol for MCCB breaker. Now let me give you a demonstration. For example, we got an MCCB breaker symbol, single line. Okay, this one is also a single line MCCB breaker symbol. This one is used for circuits with high electrical current. Then here we got a multi-line MCCB symbol containing symbols for both, well, overload and short circuits, okay? And, well, by the way, the symbol that you can see here would be the American version, based on the NEMA standards. And, guys, we have some more peculiar symbols that you can actually see here. Like, this one is used for draw-out circuits. And again, don't forget, we're still talking about the NEMA standards, the American symbols. And this one is, for example, used for fixed circuits, okay? Moving on, guys, there are some auxiliary features to these types of breakers. Like, for example, MCCB breakers actually have auxiliary contacts. All right, let me try to give you a further elaboration on this. Let's say, for example, the switch is actually on here. Let me write it down. In this case, the normally open contacts that we have would be closed, and, well, exactly in reverse, the normally closed ones would be opened. And yeah, basically this could be counted as an auxiliary feature that we have in such breakers. Also, guys, another feature or, well, a sub-item that we have in such breakers is called fault contact. Well, as you know, guys, for any reason, we might have problems such as short circuits or, well, overloading in our whole system. And this is where exactly we can use fault contacts. Now, they could be specified by numbers such as 95, 96, 97, and 98. And when the switch would be set on trip, well, these would react. And you know the drill, basically. Normally closed ones would open and normally open ones would close. And by the way, guys, when it comes to using these in control circuits, these contacts could actually be connected to signal lamps to, well, find out what exactly is going on with our breaker. Okay, guys, there's an additional feature or an item that we actually we can have in an MCCB breaker, and it is called the shunt trip. All right. Now the question is, what exactly this does for us? Well, as I said, this could be set in some of the MCCB breakers, and after that, when it gets a signal, we'll get the ability to control the switch. For example, set it on trip from a long distance. Okay, guys, so far, we got introduced to some of the most important, well, electrical symbols that we usually need when it comes to working with electrical diagrams. And now, in this session, we're going to start getting familiar with the electrical abbreviations. Now, to put it simply, guys, the electrical symbols that we would see in an electrical diagram usually are specified through particular letters. As an example, the contactors are usually, actually specified by the letter K. For example, we have KO1 here in this diagram. The switches, or more precisely actually, the circuit breakers, are specified by the letter Q. Like, for example, for MCB and MCCB breakers. I guess we have an example in this diagram. Yeah, here. Okay. The signaling devices like signal lamps are being specified by the letter H, such as here. Then we have the letter T specifying transformers in a diagram. As an example, in this very diagram, we have this transformer, which is shown through TO1. Or down here, we have another one, I guess, a CBCT transformer, and it is shown by T100. For specifying the terminals in a diagram, we use the letter X. For example, we got a terminal right over here. Okay, let's move to the next slide. In this slide, we can see a list of some of the most important abbreviations that we usually need. For example, we have F representing protection devices such as fuses and relays. And well, obviously we talked about some of these abbreviations that we have in this list, such as H or K. And for motors, we use M. Then measuring equipments are being shown by P. The breakers and, well, basically disconnectors such as MCB and MCCB are being displayed by Q. We have S for switches, T for transformers, and as you can see, it doesn't matter what kind of transformer we have, we use T for all of them. And last but not least, the terminals, which are actually one of the most important items, guys, that we have in an electrical diagram, are being displayed by the letter X. Welcome back, everyone. A very essential part of every electrical diagram would be the lines. Now, usually, guys, we can understand what each line exactly does or, well, represents in a diagram through their shape and appearance. So, obviously, in a diagram, we might see different patterns for lines, like some of them might be thick, some of them might be thin, or even dotted lines. So, without any further ado, let's talk about the different types of lines that we would see in a diagram. Alright. Usually, guys, the patterns that we would see for the lines in electrical diagrams would be one of these three. Okay, let me try to elaborate now. For example, as you can see here, for the first line, for this thin line, we have electric line or cable wire conductor of a single thread. Then, compared to the first example, or first type of line, if we had more thickness, if the line was actually thicker, we can make sure that that specific line actually representing a power line. Like when we want to display the phase lines, L1, L2, L3. Now, guys, when we want to show how many lines are exactly moving through a path, first we need to set a single line here, and then right next to it, we can write down the exact number of passing lines. And well, sometimes we might be using a shielded object, like a shielded cable. Now, to show that we are using such object in our diagram, we can use this specific pattern. Alright, we have some other usages for the lines in diagrams. For example, let's say we want to convey or show that some of the equipment, some of the items are actually set outside our electrical panel. Like, for example, let's say on the door. Well, to convey this message, we can set a line with this pattern all around our equipment. Like, for example, here, the line is set all around the electrical symbols that we have for the push buttons. They are actually connected to the terminals, but this line here shows that the push buttons themselves are set on the door, for example. Now, we also have this contact set in this frame here, and the contact is actually connected to some terminals in an electrical panel. And, well, as I just mentioned, this frame here shows that the contact itself is actually set outside the electrical panel. Okay, now take a look at this slide, guys. As you can see, we got a panel and, a diagram of a panel. And in this diagram, all the electrical equipments and, well, all the protective devices are set inside this frame here. This means that all the devices here are set in a single panel, in a single box, for example. Now, in the next slide, guys, we have another pattern of lines. This dashed dot line is usually used for showing the earth systems. Well, guys, to be 100% clear, this isn't the only usage. We have another usage as well. Mostly we use it for showing the earth systems, but another usage would be for separating two parts of a diagram. For example, when we use it, we would have two sides, interior and exterior. The interior part would be the panel, and the exterior would be the earth system. Alright, what we got here is an example of a draw-out electrical panel. Now, obviously, because we're discussing the lines, the first thing that might actually catch your eye would be this frame set all around the entire equipments in this whole diagram. This again means that all of the equipments are actually set in a single chamber or in a single panel. Now, the mentioned panel or the mentioned chamber might, for example, be this. Now, again, because of the symbols that we have, because of the patterns of lines that we have, we know that some of the equipments are set outside the panel and some others are set in the interior part of this panel. Hello and welcome everyone. Hope you all doing very well. Today we'll be starting our work regarding analyzing electrical diagrams. Before we start our work though, we need to discuss a very important and fundamental point first, alright? Mostly guys, the electrical circuits are being divided into two main segments. Segment number one is called power circuit. And segment number 2 is called control circuit. Right? Now let's talk about them and find out what exactly they are. Now, in the first segment, guys, the power circuit, we want to get an electrical power from a system. It could be a single phase or three phase, and then convert that power into a load. Now, this load here could actually be for different devices. For example, a single or three-phase motor, CNC device, section device, some sort of a forge. Basically, anything, any kind of device that we are using. Alright? And then the second segment, as I said, would be the control circuit. Now, for example, let's say this control segment, this control circuit, is being fed up through a single-phase system. And then we would have an interaction in between these two circuits, as in the power circuits get some commands from the control circuit, and the control circuit would actually get some feedback from the power circuit. Okay? Now, that would be enough for now. Later on when we started our work regarding reading and analyzing electrical circuits, we're going to understand this concept further. Now guys, let us start our work by a very simple circuit. And well, as you can see in the title here, this is actually a power circuit. Okay, let's see what exactly we have in this circuit here. Well, first off, there's this MCB breaker set right here. On this side, we have an electrical symbol, which, as you already know, this is the electrical symbol for MCB breakers. Below the breaker, we have a contactor, and down here, we have a motor, a three-phase one. Now, to put everything simply, we need to connect these lines, these phase lines, to our MCB breaker, as in L1, L2, L3, to the MCB breaker. And obviously, we need to connect the MCB breaker to the contactor, more precisely to the L terminals. Then on this side, we would have the T terminals, and they would be connected to U1, V1, and W1. Alright guys, so on the right, we have a schematic view on the whole circuit, and on the left, we actually have a realistic view on everything. Like we have the MCB breaker, the contactor, and the motor. Again, the lines would be connected to the MCB breaker, exactly like this. And then, as I said, the MCB would be connected to the contactor. And at the end, the T terminals of the contactor would be connected to U1, V1, and W1 in the motor. And yeah, that would be it, guys. That would be, this was a very simple diagram, wiring diagram of a power circuit. Now, guys, let's go through the whole circuit again. The whole power circuit again, but this time, let's actually throw a control circuit in there as well. Now, as the protective device, we have a fuse, F0. Then again, below the fuse, we have a contactor. And down here, we have a bimetal, F1 this time. Now, we can start by connecting the phase lines to the fuse first. Again, L1, L2, and L3. Okay, now, the fuse should be connected to the contactor. And right after, obviously, the contactor should be connected to our bimetal. And at the end, the bimetal would be connected to the motor, three-phase motor. All right. Now, let's go through the realistic view. Now, what we were supposed to do, that's right. First, connect the phase lines to the fuse. Here we go. Oh, and by the way, guys, the fuse could actually be any type. Now, anyway, fuse to the contactor. Then, in the next step, the contactor would be connected to the overload relay or the bimetal. And at the end, the bimetal itself would be connected to the motor. All right. Now, basically, guys, this would be a complete power circuit that we can use, or, well, in other words, that could help us start up or, well, turn on a three-phase motor. Hello everyone, welcome back. In our previous session, we went through a power circuit, more precisely, a wiring diagram of a power circuit. And in this session, we're going to talk about, or we're going to take a look at the control circuit of the same power circuit as our last session. All right, we said that usually we have a system like a three-phase system with three phase lines. Then we said that we can connect the phase lines to the fuse and then connect the fuse to the contactor to the bimetal, and bimetal to the motor at the end. So what we can understand from all of this, what we've talked about, is the fact that we actually need to start up the contactor. The contactor should be working. To do so, we need to connect a specific voltage to the bobbins of the contactor. All right, let's talk about it a little bit more. This would be the bobbin of the contactor. It has two terminals on both sides, A1 and A2. Now, A1 terminal should be connected to phase, and A2 terminal should be connected to null. Now, knowing this, or based on what we just said, we need to go ahead and design our control circuit. Let's see how. Now, when we are talking about control circuits, the first thing that we can think of would be or might be a protective device. For example, a fuse. Now, first off, one of these phase lines, L1, 2, or 3, should be connected to the fuse like this. Then the fuse itself should be connected to this starting chassis here. Start push button more specifically. Then number 4 down here should be connected to the A1 terminal in the contactor. And then, as I said, A2 terminal in the contactor should be connected to the null, like this. Now, remember, guys, this contactor is the same contactor that we used in the power circuit. So, yeah, don't get confused. We have the same contactor here, the same device, Now, guys, when we start pushing this push button down, phase would reach or would be connected to A1 in the contactor. And as I said, A2 is connected to null already. And overall, the contactor would start working immediately. And as a result of this, the motor would be working. Would start working. Okay, moving on. Let's see what else we can discuss here. Well, the electrical diagram, or rather electrical symbols that we have in a diagram representing control circuits would be this. There's phase, fuse, then the start push button, A1 terminal and the contactor, A2, which is connected to the null. And basically, guys, in an electrical diagram, we can find these symbols, most specifically, the symbols representing control circuits next to the symbols that we have for power circuits. Alright, guys, welcome back. In this session, we're going to continue our discussion regarding control circuits. There are some complementary points regarding them that we can talk about. If you remember from our previous sessions, we said that in a contactor, we usually have several types of, actually 2 types of contacts. Well, we have, for example, the power contacts, which would be these. Let me point them out. And then we said that we would have an auxiliary contact in between terminals 13 and 14, for example, like this. Okay? And we also said that when the bobbin of the contactor, talking about the A1 and A2 terminals in the contactor, starts getting this incoming voltage, like for example 230 amperes of voltage, AC voltage, all of these contacts would be closed. Talking about both of the power contacts as well as, let me point them out again, as well as the auxiliary contacts set in between 13 and 14 terminals. Now, guys, in this session, we're going to see how exactly these contacts are affecting, or well, actually are being used in a control circuit. Okay, let me go to the next slide. All right, take a look at this. As always, we have this power circuit here. And, well, you know how it goes. The phase lines L1, L2, and L3 would be connected to the fuse first. And the fuse would be connected to the contactor to the bimetal, and bimetal to the motor. To the terminals of our 3-phase motor. Now, next up, as I said, we need an incoming voltage connecting to the bobbin of the contactor. Well, obviously, to the A1 and A2 terminals. Now, in addition to all of this, I've actually added this stop push button here, to this whole circuit, and don't worry, we're going to talk about it. Now, let's see what we can do here. I'm going to get a phase and connect a phase from this L1 to the fuse, like this. And then, fuse would be connected to the stop push button. And stop push button would be connected to start push button. Now, start push button would be connected to A1 terminal in the contactor. And as always, the A2 terminal and the contactor would be connected to the null. Now, if we go ahead and start pushing this start push button down, the contactor would start working. More precisely, the contacts here would start working, and as a result of all of this, the motor would obviously be turned on. Okay, and when we stop pushing this button down, obviously, again, the contactor would stop working, it would be cut off, and the motor would be turned off. All right. Now, guys, let's say we have successfully started the motor. We have turned the motor on. The question is how we can keep it that way. In other words, how exactly we can keep the motor running. Okay, let's see how. Well, if you remember, we had a couple of terminals here called 13 and 14. We need to connect these to our start push button. Let me just draw the sketches that I had before. Okay. Now, what we should do? Well, 13 would be connected to 3 here, and 14 would be connected to 4. Now, if we go ahead and start pushing this button down, the contactor obviously starts working, but this time there's a difference. These two contacts, 13 and 14, would start working as well. Alright? And when we stop pushing it, when we pull our finger up, the electrical current will go through a path like this. It moves all the way from here, through here to the contactor, also through the contacts, and it continues following the path all the way to A1 terminal in the contactor. And as a result of this, the contactor would stay on. So we somehow made this permanent. We don't need to use our finger for pushing and pulling every time. Alright, now let's take a look at the wiring diagram or the electrical symbols that we have for such circuit. As you can see, we have the contacts here, 13 and 14. Talking about these two. And they are connected to the contacts 3 and 4 in our start push button. And somehow created an alternative path for our electrical current. And well, as I said, this would start up the contactor, this would turn on the contactor, but this time it would be permanent. Alright. By the way, guys, these types of control circuits, let me mark it out. Okay, these types of control circuits are actually one of the most important and common circuits that we can use in the entire field of electricity today. Welcome back, everyone. If you remember, previously we discussed an equipment called overload relay or bimetal. And we saw how we can use this equipment in a power circuit. Just as a quick reminder, if you remember, we had 3 phase lines. Let me write them down. L1, L2, and L3. And we said that these lines would be connected to contactor. Let me try to draw a symbol for the contactor as well. Okay. And we would connect the contactor to the overload relay. And then at the end, the relay was connecting to the 3-phase motor. And basically this was the diagram that we would have for overload relay or bimetal relays in power circuits. And also, if you remember, we said that we have some additional contacts, a couple of normal open and normal closed ones. And we said that based on how the relay is exactly functioning, the open contacts would be closed and closed contacts would be open. Now, in this session, guys, we want to find out what kind of role does this normal closed contacts that we have exactly play, in turning on the 3-phase motor. So let me move on to the next slide and start our discussion. Okay, so the power circuit actually works exactly the same. there's no difference, nothing has changed. So let's talk about the control circuit instead. So again, L1 would be connected to the fuse. Then we need to connect the fuse to 95 contact set in our bimetal. And then we need to connect this contact 96 to stop push button, then stop to start, and start would be connected to A1 in the contactor. And well, the A2 in the contactor would be connected to the null. And don't forget these two contacts, 13 and 14. These two contacts should be connected to contacts 3 and 4 in our start push button. Now guys, remember, in our power circuits, if the overload relay or bimetal, in other words, starts working, the contact, its contact in the control circuit would be opened, and as a result of this, the contactor would stop working. So, overload relay or bimetal could actually cut off the contactor and as a result turn off the motor, and also it could be set in the electrical current's path in the control circuit. And well, after these contacts started working, talking about 95 and 96, the contactor itself again stops working. Okay everyone, welcome back. Up to this point, we said that when it comes to using electrical symbols, we can work based on some specific standards. For example, IEC, and we also mentioned an American standard called NEMA. And, well, we've actually seen some of these American symbols as well. For example, this was the American symbol that we would use for overload relays. Then also the contactors. The contactor alongside its bobbin and its contacts. Then the start button, for example, or the stop push button. Normal open contact, and also normal closed contact. Now let's take a look at a circuit containing these symbols. All right. First off, guys, when we are working based on this specific standard, we should know that we don't have any lines representing null. And also, as another point, most of the sketches in the electrical diagrams would be set horizontally. All right? Now, here we have 3 phase lines, L1, L2, and L3, which are connected to contactors, and the contactor is being connected to overload relay, and overload relay or the bimetal would be connected to the motor. To the terminals that we have, T1, T2, and T3. And we also have a control circuit here. First off, the control circuit is being fed up by 2 of the phase lines. Like, for example, here by L1 and L2. And also, guys, another thing that might actually catch your eye would be the order of setting the equipments. If I want to elaborate here, the order is actually different from what we used to see in IEC standard. For example, the stop push button is set here, And on this side, we have the bimetals or the overload relays normal closed contact. And you can also see the terminals 95 and 96. Here we got the contactors bobbin, then the start push button, and then here we have the contactors and its contact with numbers 13 and 14. Let me write it down. So guys, the circuit that we had before was kind of like this. Like we should have a fuse. Let me set this here as the fuse. Then the normal closed contact of the bimetal. After that, the stop push button. Then the start push button. After that, the bobbin, A1 and A2, and the null. And then here, contacts with numbers 13 and 14. One difference that is quite obvious is the fact that this diagram here is actually vertical. But here in the American version or NEMA, it is set horizontally. And also some of the equipments are set in another place, but this isn't a big deal. Okay, now let me move to this slide. All right. Now guys, before we start talking about our next circuit, first let's have a discussion on MCC switchboards. All right. So let's see what we have. There's a three-phase motors starting circuit that is set inside of a panel, and the panel is actually has this drawer shape. So, in other words, all of the equipments here are set inside a drawer. Now, when we draw the panel out, the circuit would actually be disconnected. And also, in the backside, the backside of the panel or this drawer, we have some connections through which the panel would be connected to the three-phase motor or three-phase lines. All right. Now, guys, let's go ahead and take a look at the interior circuit that we have in this electrical panel. Well, actually, by looking at it, let's try analyzing it. All right, take a look at this, guys. Here we got a diagram of an electrical circuit from one of those electrical panels, draw out electrical panels. It is called MCC wiring diagram. And by the way, guys, MCC stands for Motor Control Center. Now, first off, we have the phase lines here. And through the connections that we would have, they would be connected to the breaker that we have. And the breaker could, for example, be MCCB breaker. Then after that, the breaker would be connected to the contactor. Then from the contactor to the overload relay. And at the end to the three-phase motor. Now guys, as we previously mentioned, we can use two of the three-phase lines like L1 and L2 for feeding the control circuit. We'll get an incoming voltage from these two lines, L1 and L2. Then here we have two fuses, but we can also use one. Then right after we have this transformer, a decrescent transformer, which decreases the voltage for feeding the control circuit. All right, now as you can see, there's another fuse here. And then everything is connected to the control circuit. Now, regarding the circuit itself, the control circuit itself, we have this stop push button. And, well, it is actually quite the same as before. I mean, we have the start push button after that. And then here we got the contactors button. And here we got the bimetals normal open contact. And again, the same numbers as before, 95 and 96. Here we got the normal open contacts of the contactor with the same numbers as before again. I mean 13 and 14. And they are connected to the start push button. We also have some signal lamps, guys. When the contactor starts working, these lamps here would be turned on. Okay, and we also have another signal lamp set up here on this line. And if the contactor was turned off, or if it was diffused, for example, this contact here would work, and this makes the signal lamp to be turned on. And if the contactor was activated again, the contact here would be opened, and as a result, the signal lamp would be turned off. Now, guys, remember, the signal lamps and also the push buttons, I mean, talking about the start and stop push buttons both, they are all set on the exterior part of our electrical panel. Talking about the front part or front panel of the unit or the drawer. And, well, here you can see all of their electrical symbols. I mean, for the signal lights and also for the start and stop push buttons. Welcome back, guys. In this session, we'll be focusing on another type of electrical circuits, and we can claim that these circuits are one of the most useful ones in the whole electrical diagrams. The circuit is called forward reverse. Now, guys, forward and reverse are actually two modes that we have for motors, for example, for three-phase motors. And in this session, we basically want to see how we can change in between these two modes. For example, let's say we want to convert a forward three-phase motor into a reverse one. To do so, two of the three phase lines should be displaced. Alright, let me elaborate on this. Let's say, for example, L1 is connected to U1, L2 to V1, and L3 to W1. In this case, the motor would be forward. Now, if two of the lines, as I said, like L3 and L2 were to change places, the forward motor would be converted into a reverse one. Now, there's a question here, guys. What's the role of the contactors? I mean, how exactly they would function? Well, to understand this or to find out, let's do something. I'm going to connect L1 here to L1, then L2 to L2, and L3 to L3. And let's just assume that for now we are not using a bimetal. In this case, T1 would be connected to U1, then T2 to V1, and at the end, T3 to W1. And this would be the wiring system for a forward motor with contactor, or I guess it's better to say this is how a contactor works in a forward motor. Alright, let me write down F here so that I won't forget, and move on to the next. Let's see how contactors work in the second type of the motor, like the reverse type. So, L1 would be connected to L1 again. L2 would be connected to L2. And line number 3 would be connected to terminal number 3 or L3. But what we are going to do next would be different from what we did before in the last type of motor. Different how? Let's see. T1 would be connected to T1. Then T2 would be connected to T3. Okay. And obviously T3 would be connected to T2. Now, in this case, if the motor started working, if the contactor started working, the motor would be reversed. By the way, guys, remember, we can't have these two types of contactors working simultaneously. In other words, we can only use one of them each time, either the forward one or the reverse one. And overall, guys, this is what we call the forward-reverse three-phase motor power circuit. And well, by the way, we also have a control circuit for these types of motors as well, and we're going to talk about it later on in our course. All right, everyone, welcome back. In our previous session, we saw how a forward-reverse motor power circuit works, and today in this session, we're going to go through their control circuits. But before we start doing that, let me add some more equipments to the power circuit that we have. Equipment such as fuses, as well as an overload relay. Now, we can start our work by connecting the phase lines to the fuse, starting by L1, like this. And fuse would be connected to the contactor. Then L2 to the fuse, and then to the contactor. And well, the same goes for L3. Now for the terminals down here. T1 L1, T2 L2, and T3 L3. And then the overload relay or the bimetal would be connected to the terminals in our three-phase motor. Now the contactor. L1 here first would be connected to L1 terminal in the contactor. All right. Then the second phase, L2, to this terminal. And the third phase, L3, to here. Now, down here, again, phase 1 to phase 1, like this. Then phase 2 to phase 3. And obviously phase 3 to phase 2. All right. Now, we need a start push button for turning this contactor on. And by doing this, our motor would actually be a forward motor. And we can also use another start push button, this time for this contactor. And if we use this push button, this contactor overall, our motor would be the reverse type. Now, guys, this would actually be the part that we need to design a control circuit. A circuit such as this. We need one of the phases here. For example, let's say L1. And also, we need a fuse. Then a bimetal normal closed contact. Then after that, we need a stop push button. And after this part, our circuit would be divided into two parts because, well, we have two separate contactors. And you know what they are. One of them is for the forward motor. The other one would be for the reverse motor. Alright, so first, let's connect this to the start push button here. Then after that, connect this to A1. And after that, A2 and this contactor would be connected to the null. And as always, contacts 13 and 14 would be connected to contacts 3 and 4 here. Now we can connect them directly like this, or we can use this method like this. Now we kind of need to do the same thing for the reverse motor. First, connect this to the start push button, then start push button to the bobbin, A1 in the bobbin, A2 to null, and then connect these contacts as well. Now, if we use this push button, if we push this one, our motor would be a forward one, and also this contact would be closed and the contactor would remain forward. Now, for converting the motor into a reverse motor, first off we need to use the stop push button. Alright, and then after doing that, we can push this button, this start push button, and after this, the motor would work as a reverse motor. Now guys, during our course, we're going to go ahead and add more equipments to our circuit quite gradually up until the point that the two contactors somehow start working together simultaneously. Welcome back, guys. In this session, we want to add more protective equipments and devices to our control circuit. Now, guys, if you remember, we said that in contactors, we basically have different types of contacts. And, well, as you know, we have the main contacts, the power contacts, and then there was the auxiliary contacts as well, like 13 and 14 here. Okay? And then also we said that we have some contactors with more auxiliary contacts, like 21 and 22 here. Now again, if you remember, we would have called this contact normal open, and this one normal close. We said that when the contactor started working, the power contacts would be closed, this auxiliary contact would be closed as well, but the normal closed one would be opened. Now, what we want to do here would be using this contact, this normal closed contact, in a forward-reverse motor circuit. Okay, so this would be our purpose today. Let's see how. Now, we talked about the power circuit in our previous session, so we're not going to draw or design it again. And instead, let's just focus on the control circuit. Alright, let me just do something real quick before we start our work. Alright, so we're basically going to use the same control circuit as before. Like, for example, the normal close contact in the bimetal would be connected to the stop push button, and then the button would be connected to these two start buttons for these two separate contactors. And we need to connect the 13 and 14 contacts as well. And, well, basically nothing new is going on here. More precisely, nothing new up to this point. The newly added item here would be this closed contact, this normally closed contact that we set in the path of the electrical currents in both contactors. What does this exactly mean, though? Well, we got a contactor here called K1M. Now, this contactor has a normal closed contact which is now set in the electrical currents path here. Alright? Now guys, when the contactor starts working, when it gets activated, its normal closed contact that is now set here, as we said, would be opened. And this means that from now on, we cannot use this push button here, this start push button, to convert our motor into a reverse motor. Okay? And well, guys, obviously the same thing is happening for the second contactor. I mean, we've set the normal close contacts of this contactor here in the path of this contactor, like this. Okay, let me select this. Now, just like before, this time when this contactor, the second contactor, gets activated, its close contact that we set in this path would be opened. And again, just like before, from now on, we won't be able to use this start push button to activate the second contactor, which is actually the forward contactor. Somehow the close contact here prevents you from doing that. And well, obviously the same thing is happening in the other one. Alright, overall guys, this is what I meant by adding more protective equipments and devices to our control circuit. Alright guys, so far we learned that we are able to convert our motor from a, for example, forward motor into a reverse one. Now, sometimes we might have to do this conversion with more pace. In other words, the conversion should happen faster. Now guys, to achieve this goal, we actually need to use a new circuit. However, before we start talking about this new circuit, let's get introduced to a new equipment called double push button. Now, to put this simply, guys, a double push button would be an equipment consist of two other push buttons, a start push button as well as a stop push button. Let me write this down. Okay. Alright, so this was a very short definition on this equipment, and this would be its image, obviously. And I also have a clip here. Let me play the clip as well to get a better view on the whole device. And well, regarding their colors, guys, these push buttons could either be red or green. Okay, moving on. Alright, now let's see how exactly these equipments work. Now, as you can see, we have these contacts here. If we don't push the button down, this contact, number 3, would remain open, and the other one, number 1, would remain closed. And again, guys, we have two types of contacts, normal closed and normal open and normal closed here. But if we start pushing the button, contact 3 would be closed, and contact 1 obviously would be opened. Now, guys, take a look at this side of our slide here. We got the American symbol for our equipment. The electrical symbol for double push buttons based on NEMA standard. And we actually have the two modes here, when we don't push the button and when we push it down. Now guys, another question, what is the exact usage of this equipment? Now, if you remember at the beginning of this very session, we said that we want the conversion in the motor to happen faster. And this is where exactly we can use this button. More specifically, guys, before we would have used two separate contactors, one for forward, the other one for reverse. But now, we've actually done something else here. There's a phase line connected to one side of this push button here, and the other side of the push button is connected to both of the contactors, both forward and reverse. Now, based on this current diagram, before we start using the push button, the forward contactor is deactivated, and instead the reverse one is working, okay? So we can say that this is actually the normal mode of this system here. Now, if we go ahead and start pushing this button down, the forward contactor would be activated and the reverse one would be deactivated. And remember guys, as we have written here, this whole process will be done momentarily, okay? Later on in our future sessions, guys, we're going to see how we can use this double push button to do this conversion as fast as possible. I mean, most specifically, convert the motor from its forward mode to reverse, for example. Welcome back, guys. In this session, we're basically going to continue our discussion regarding faster conversion in between forward, reverse motors, and also we're going to take a look at an MCC panel, or in other words, motor control center panel. And well, we're going to discuss how this whole concept of fast conversion would be applied on it. Now, first off, let's go through the panel itself. Let's see what we have here. First and foremost, guys, this circuit that we can see here, this diagram, is for a control circuit. Let me write it down. Now, this control circuit is set in between two phases, L1 and L2, which are actually feeding this control circuit. We have this stop push button, and on this side, we have a normal closed contact of an overload relay, or a bimetal. And as you probably already know, the contacts are 95 and 96. Now, this whole pattern here, let me mark it down. This is the pattern for a double push button of a reverse contactor. And we also have another one, but this one is actually for a forward contactor. Now, as you can see, in the path of this forward contactor, we have a normal closed contact for this push button. I mean, for the reverse one. Okay. And well, the same thing is happening for the reverse one. I mean, there's a closed contact, a forward closed contact set in its path. So, guys, what we can get from all of this is the fact that normally, if we go ahead and push this forward button down, double push button, and reverse is actually closed, by the way, this contactor would be activated. And if we go ahead and push this push button down, this would be opened, and this contactor would be deactivated. And then also, this contact down here would be closed, and as a result, this contactor, the reverse contactor, would be activated. And well, the same thing happens in reverse. If we push this one down, forward would be activated and reverse would be deactivated. Also, we know what these contacts are. These are 13 and 14. What else we can discuss? By the way, this contact is for this contactor here. It is related to this contactor. And the other one is related to this contactor down here. Now, for further protection of this circuit, the closed contact of this contactor has been set here, and the closed contact of this contactor has been set in this point. Oh, and by the way, don't forget the signal lamps. We have these signal lamps which would specify which contactor is working, the forward one or the reverse one. Okay, moving on. Now, let's go through the interior circuit of a MCC panel. If you remember from our previous sessions, we said that on this side we have the push buttons. More specifically, this is where we can call the front panel. The front panel of our MCC panel. We have the push buttons, both stop and start, and also the signal lamps. And then, on this side, first we have the phase lines entering the panel. Then we have this MCCB breaker. We could have a fuse here as well. Alright, next up we have the forward contactor, as well as the reverse one, an overload relay, and the motor. For feeding the control circuit, we have used L1 and L2 phases. Also, we got 2 fuses, as well as 1 decreasant transformer, which would decreases the incoming voltage in the control circuit. Now, exactly the same as the circuit that we had in the last slide, we have a stop push button here, and also this close contact of the bimetal, 95 and 96. And we have this reverse push button, and also the forward push button. And we already talked about how exactly they would work. And again, we have the close contacts of each contactor set in the path of the other or the opposite contactor. You can see the signal lamps that would actually function based on how the contactors, the forward and reverse contactors would work. And as I said, the lamps are set on the front panel. Alright guys, so basically this is an example of a fast forward-reverse circuit that we might find in a motor control center panel, or, well, in other words, the MCC panel. Hello and welcome back everyone. In our today's session, we're going to start a new topic. We're going to have a discussion regarding air fault protection in 3-phase motors. Okay guys, let's assume that we got a 3-phase motor. It's working, it's running, it's getting this incoming electrical current, I1, 2, and 3 from our 3-phase system. Now, in such case, in such situation, we usually say that we have a balanced current. Now guys, for any sort of reason, let's say the coils that we got and the motor itself are interacted with the panel of the motor and then with the earth, okay? This way, a fault current would be created. In this situation, in this case, that a fault current has been created, we say that we have an unbalanced current. Now, an unbalanced current could cause the motor to overheat, and for example, this could ruin your coils completely. Now guys, to protect our motor from, against these unbalanced currents or these false currents, we actually need to use some new devices, some new equipments. The first device that we can use would be core balanced current transformer. We've actually seen its abbreviation before, CBCT. Now, when we want to connect our 3-phase system to our motor, the electrical currents should actually move through our CBCT transformer. And by the way, a CBCT transformer has a shape like this. Now, what is the duty of this equipment? We said that we would have a current coming from these phases, I1, 2, and 3. When the current becomes unbalanced, more specifically when we have a fault current in our 3-phase motor, we would get a small signal, for example here. And well, obviously through this signal, we would understand that we are actually having this air fault in our motor. Okay, moving on to the next slide. Guys, if you remember, when we were discussing MCCB breakers, we said that inside these breakers, an equipment would be set called shunt trip. Now, if we connect a signal to both sides of this relay here, let me point them out. Talking about these two, okay? This could cause the MCCB breaker to be set on the trip mode. I write it down. Now, guys, the thing is, we can use all of these mentioned equipments. I mean, CBCT transformer, shunt trip, and also MCCB breaker for further protection regarding our motor. How? Let's see. Let me move to the next slide. All right, take a look at what we have here. We got some electrical symbols in this diagram. For example, this one is for the MCCB breaker as it is written actually. And then up here we have the three phases, L1, 2, and 3, which are connected to the breaker. And then, as I said, the electrical current would move from the breaker and right through the CBCT transformer and all the way to the three-phase motor. And well, as you probably already know, we have the earth down here. I mean, more precisely, the connection in between the motor and the earth. All right, back to our discussion, guys. Let's say for any reason, a fault current has been created. I mean, in other words, we have an earth leakage. In this case, a very small current would be created in between the motor's frame and the earth. Now, because of this leakage, because of this current leakage, we would get a signal on both sides of our CBCT transformer. Now, the CBCT transformer would be connected to this relay called earth fault relay. And now, through the outgoing current of this earth fault relay, the shunt trip set inside our MCCB breaker would be activated. In other words, the breaker that was actually on so far would immediately be set on trip. And well, as a result of this, the electrical current would be cut off and our three-phase motor would stop working. It would be turned off. Right, guys, so basically, this is how you can protect your three-phase motor through using equipment such as MCCB breaker, CBCT transformer, air fault relay, and also shunt trip relay. Now, guys, we are also able to do something else. Let me change the slide. Okay, guys, take a look at this diagram. The thing is, sometimes inside the relays, we would find a normal closed contact, like this. All right, now, once again, the three phases L1, 2, and 3 would move through the MCCB breaker, and then they would enter the CBCT transformer right in the middle again. Then they would be connected to the contactor, and from the contactor to the motor. Now, let's say the CBCT transformer is giving this signal, and the signal is actually connected to the air fault relay. And as I said, inside the relay, we have this normal closed contact that is actually set in our control circuit electrical currents path. So, as a result, guys, we can simply use this start push button here to activate this contactor. Okay, now guys, once more, for any kind of reason, it doesn't matter what, if we ever got any fault current, we would get this signal here, more precisely, a positive signal here. And this positive signal causes the normal closed contact to be opened, and then the electrical current would be cut off, the contactor would stop working, And as a result of everything, the motor would be turned off. And yeah, guys, basically this would be another method that we can use for applying further air fault protection in our three-phase motors. Now, let me give you an example. I'm going to show you a real diagram on regarding this whole concept. Okay, we have this diagram for a real control circuit. Up here, we have the three phases entering our electrical panel. Then here we got this manual switch. After that, we have this MCCB breaker. And then the transformer, the CBCT transformer. And well, obviously the transformer is being connected to the air fault relay here. And well, there's this contactor here that we would use for turning on the motor, the three-phase motor. Okay, what else? We have this overload relay, that's by metal. And also we have the CBCT transformer signal that would be connected to the air fault relay. And also, as I said, we have this normal closed contact set in the air fault relay. And the address that we have for the terminal set in this contact would be 0/J9. Alright, and the address is actually pointing towards this point here. We talked about this before. Based on the zones, we have J9. So guys, when the CBCT transformer gave us a signal, the air fault relay would be activated. More specifically, its normal closed contact would be opened. And as a result, the signal to the contactor would be cut off, and well, obviously, the contactor would stop working. Alright guys, so basically, this would be how exactly you can use equipment such as CBCT transformer and also air fault relays regarding the matter of air fault protection in three-phase motors.